about going on the job market this year.
Thank you. All right, so hi, my name is Raja, and today I'm going to present our work on evolvability for inter-domain routing. This was joint work with David Tran Lam and Aditya Kella from the University of Wisconsin and Peter Steenkiste from Carnegie Mellon University. So to start this talk, I want to quickly summarize our work in a single slide. The key question our work aims to answer is what features are needed in any inter-domain routing protocol to bootstrap evolution to new inter-domain routing protocols. By bootstrap, I mean facilitate their deployment across non-contiguous domains, and if desired, gradually deprecate existing protocols in favor of one or more new protocols. We found that two really modest features were sufficient to enable evolvability. The first is pass-through support, which allows ASs or routers to transitively convey information about protocols they don't support to their neighbors. The second is a carefully systematized multi-protocol data structure that allows a huge diversity of routing protocols to participate on end-to-end routing paths. To understand the benefits these features could provide, if they had been included in BGP, we created an extended version of it called D-BGP. We found that D-BGP can facilitate an internet comprised of many inter-domain routing protocols. And let me step back here and introduce BGP and why evolvability is so important. So the inter-domain routing infrastructure is this really important part of the internet's architecture. It allows end users to access content by creating routing paths in the control plane between destinations interested in receiving traffic, such as end users' ISPs, and sources interested in sending traffic, such as YouTube and Google. Today, this routing infrastructure is provided by a single protocol called BGP. So what you see on the screen is a simple internet topology. Circles are autonomous systems, or ASs, which belong to one or more ISPs. BGP creates routing paths by sending reachability advertisements upstream from destinations to sources. The sequence of ASs traversed by advertisements forms the routing path. When a router receives multiple path advertisements for a destination, as is the case for the top right AS in the picture, it picks a single best one to disseminate further upstream. The path contained in this advertisement is called the best path. In this case, it picked the rightmost advertisement. Once the source has a routing path to a given destination, it uses IP to send traffic along it. So unfortunately, this really important protocol has many well-known problems. For example, it can't limit the amount of incoming traffic to ASs. Its routing paths are slow to converge in the face of failures. It provides no quality of service guarantees, and it robs sources of path options by indiscriminately choosing a single best path per router. In response to these issues, the research and network operator communities have proposed a variety of these really great new protocols to address these shortcomings. Some are listed on the screen. Unfortunately, very few, if any, of these great ideas are being deployed. In this work, we argue that a key reason that new protocols have not been deployed is a fundamental problem with BGP itself. Specifically, it is very rigid. It requires neighboring ASs to use the same protocol, that is BGP itself, to create routing paths. This rigidity has made it difficult for internet to change or evolve, making Charles Darwin really, really unhappy. BGP's rigidity makes it difficult for the internet to evolve because it means new protocols must be deployed in isolated islands of one or more contiguous islands, as shown by the orange regions in the diagram. These islands can use the new protocol among their constituent ASs. But these islands must use BGP across ASs that support only BGP. This means that different islands running the same new protocol can't discover one another, disseminate new protocols control information to one another, or use a new protocol to route traffic amongst each other. This isolation reduces the benefits that can be achieved by deploying a new protocol. Hence, it reduces operators' incentives to deploy it in the first place. One common way to circumvent BGP's rigidity is to use tunnels in the data plane to forcibly, that is without support from BGP, route traffic via islands that have deployed a desired new protocol. These tunnels can be established by mechanisms out of band of BGP itself. On the screen, you see a tunnel path to the destination in orange and the best path chosen by BGP in black. Unfortunately, tunnels hide destinations' true addresses from ASs that have not deployed the desired new protocol. As such, tunnels may interfere with these AS's policies and increase their costs. In the example shown, it will force the leftmost transit AS, marked T, to use an expensive provider link to route new protocols traffic to the destination instead of the free peering link. This incentivizes AS's operators who are not currently interested in deploying a given new protocol to push back against this development, especially when it's still being standardized or while it's not yet gained a strong foothold. So here are some of the main contributions of our work. First, we found that pass-through support and a carefully systematized multi-protocol data structure are sufficient to bootstrap evolvability to a wide range of inter-domain routing protocols. These features make data plane tunneling to connect islands optional depending on the needs of a given protocol. Second, we designed and implemented a minimally extended version of BGP called Darwin's BGP, or D-BGP, that includes these features. One of the coolest results here is that it turns out that D-BGP is not that far from BGP today. For example, a basic implementation of D-BGP required only 900 lines of code in Quagga, an open source router. Also, BGP already includes one of the needed evolvability features, pass-through support, via its optional transitive attributes. Third, we characterized the benefits D-BGP could provide if it were deployed internet-wide instead of BGP. We showed that D-BGP can enable a rich internet comprised of many inter-domain routing protocols, and we also showed that D-BGP incentivizes adoption by accelerating the rate at which adopters of different types of protocols see those protocols' benefits compared to BGP. So first I'll describe how we identified the evolvability features. So to identify the needed features, we first envisioned what an evolvable internet would look like. We then systematized what support 14 recently proposed inter-domain routing protocols would need to be deployed across non-contiguous islands in this internet. We found that we can map the protocols into 3 evolvability scenarios that differ in their goals, needed control and data plane support, and operators' incentives for deploying them. We consider 2 types, both incentives for operators interested in deploying a new protocol and ways to avoid pushback from operators not currently interested in deploying it. These differences inform scenario-specific requirements any features for enabling evolvability must satisfy. We combine these requirements with global requirements necessary to facilitate an internet running many diverse protocols, and then reason about what evolvability features would be sufficient to satisfy them. So first, I want to show you what the evolvable internet we envision looks like. So here's the evolvable internet. There are only 2 things I want you to get out of this picture. First, this evolvable internet can run many inter-domain routing protocols that are each only partially deployed. The topology in the screen shows recently proposed protocols from the literature, but others could also be deployed. This internet could converge to a single inter-domain routing protocol, perhaps because operators find that protocol super useful, or it could continue to exist in this heterogeneous state. Second, to maintain global connectivity, all domains must support routing using a baseline routing protocol that is deployed internet-wide. Today, this baseline protocol is BGP. In our evolvable internet, it will be D-BGP. Some ASs may only run the baseline marked by B in this diagram. I also need to emphasize the following terms because they're really, really important for the rest of this talk. Right? Islands are contiguous groups of ASs that have deployed a given new protocol, and gulfs are the set of ASs that separate 2 islands that have deployed the same new protocol. So you see on the screen that there are 2 islands for Scion, and there's a huge gulf comprised of ASs running very different protocols that separates these 2 Scion islands. So in this slide, I'm going to put up a simplified taxonomy of the scenarios we identified and the resulting requirements. So I'm just going to put everything up. So here they are. So the first scenario is suited for deploying modified versions of BGP internet-wide. Examples include Wiser for limiting ingress traffic to ASs by disseminating extra path costs, and RBGP for disseminating backup paths during BGP convergence. The second scenario is suited to deploying value-added services in parallel with BGP. Examples include Miro for selling alternate paths to BGP's best path, and Arrow for selling arbitrary inter-domain services. The third scenario is suited for deploying protocols radically different from BGP internet-wide. We call this the future internet architecture, or FIA scenario. Note that the FIA scenario and the modified BGP scenario have the same incentives and requirements. This is because both have the same goals, to replace BGP entirely. So to provide some more intuition about how we arrived at the requirements for these scenarios, I'll talk about the FIA scenario in detail and provide a specific example. I don't have time to go into details about the second scenario, which involves deploying value-added services in parallel with BGP. Just note that the requirement for it is enabling widespread discovery of the services being sold. All right, so let's look at this FIA scenario. As I said, this scenario is suited for deploying very different protocols than BGP. These protocols typically disseminate extra or completely different control information than BGP in order to operate network functionality that BGP does not support. Examples of such control information include multiple paths per router or just link states. In terms of incentives for deployment, ASs that have some interest in deploying one of these protocols will do so if they can leverage the benefits of that protocol quickly. ASs that aren't currently interested in deploying new protocols will not push back against their deployment if they're given joint control over routing decisions. So requirements follow from these incentives. These protocols' control information must be sent across gulfs to incentivize interested ASs. And in addition to avoiding data plane tunnels, these protocols' control information should be sent in band of the baseline to provide non-interested ASs some visibility and control. This would allow these ASs to understand what protocols are used on the paths they advertise, and perhaps filter paths that use buggy ones. So to make things a bit more concrete, let me tell you about the challenges associated with deploying SION, which is a protocol suited to the scenario on today's internet. So SION is a protocol that provides source-controlled path selection. It disseminates multiple paths to destinations per router and selects which ones they want to use and allows sources to select which ones they want to use by encapsulating their path choices in packet headers. On the screen, there are two islands that run SION. They're separated by a gulf that runs today's baseline, BGP. In this topology, ASs within the rightmost island can advertise multiple paths to the destination among each other. Note that the AS at the border of the path-based of this island, marked B, can receive two paths from its neighbor through a single border router. But because B's neighbor in the Gulf uses BGP, it must use BGP to send advertisements to that neighbor. This means that it can only advertise one of the two paths options to the source island in the diagram. Exposing both path options lets the source choose which one it wants to use, requires disseminating control information for both of them across gulfs. Doing this without tunnels or out of band, but rather in band of the baseline, would give the Gulf AS more control and visibility. Once the source has been advertised both options, it can encapsulate data packets with both an IP header to cross the Gulf and a SION header to encode its path choice. So our example just now was about deploying an individual protocol. So let's look at global requirements necessary for an evolvable internet that's actually running many inter-domain routing protocols at the same time, right? So first, note that in an evolvable internet, any end-to-end path from potential sources to destinations is jointly controlled by many diverse routing protocols. One example is the end-to-end path shown on the screen. This leads to our first global requirement, which is to tell islands and gulfs of what inter-domain routing protocols are used on routing paths so that they can make informed decisions. Second, note that different routing protocols may state their within island paths in very different ways. Right? For example, link state protocols may disseminate only link adjacencies, whereas path vector protocols state the path as a sequence of AS numbers. So in order to create these end-to-end paths in the first place, there must be some lowest common denominator that allows end-to-end paths to be expressed in a way that all protocols, including the baseline, can understand. This is the second requirement. So I'm going to show the requirements and how the two evolvability features satisfy them. On the right, you see the requirements we just discussed. In a world running just one or two BGP-like inter-domain routing protocols, pass-through support within the baseline would be sufficient for all of them. Because it would transitively convey information about routing protocols a given router or AS does not support to those entities' neighbors, it would mean control information is disseminated across gulfs. By definition, this information would be sent in band of the baseline. In-band dissemination would also enable widespread discovery of islands selling value-added services. For an internet running many diverse inter-domain routing protocols, we also need a carefully systematized multi-protocol data structure to inform islands what protocols are used on end-to-end paths, to encode their control information, and to provide a common denominator to express the end-to-end path. To satisfy the first three evolvability requirements, this data structure must be passed through. So next, I want to spend a few slides discussing D-BGP's design. D-BGP is an extended version of BGP that incorporates both evolvability features. Its integrated advertisements, or IAs, extend BGP's advertisements with the multi-protocol data structure. Its processing for IAs extends BGP's processing to provide pluggable support for multiple inter-domain routing protocols, and it also provides pass-through support for all protocols on the paths chosen by individual ASs and islands. With the evolvability features integrated, D-BGP's advertisements become shared containers that can carry multiple inter-domain routing protocols. These containers are carried across gulfs by the path selection decisions of the ASs within them. So I want to spend a few slides discussing the format of D-BGP's IAs. I'll focus on its path vector field, as it provides a common denominator necessary to express end-to-end paths across a diverse range of routing protocols. So, like BGP's advertisements, IAs name a single end-to-end path to a destination. The first field in the IA is the path vector field. It is responsible for stating the end-to-end path and enabling loop detection. It extends similar functionality provided by BGP. Like BGP, individual ASs can encode their AS numbers in the path vector to state the path. But D-BGP's path vector also includes two additional extensions. First, it admits island IDs. These allow islands that can't express their within-island paths using AS numbers to participate in the end-to-end path. One example is islands that run link state protocols, which don't disseminate AS-level information. Second, D-BGP repurposes BGP's set relationships to allow islands that expose multiple within-island paths to participate in the end-to-end path. Set relationships state that only a subset of the ASs listed in the set will be used on the end-to-end path. They prevent other islands and ASs from falsely discounting the path during path selection because it appears too long when it actually isn't. So let's quickly go through how the path vector is encoded for a portion of an end-to-end routing path for the topology shown. The path traverses a Scion island, a HLP island, which uses link state internally, and a D-BGP AS. Since link state does not disseminate AS-level information, ASs are not shown for the HLP island. For this path, the D-BGP AS need only insert its AS number because it's just running an extended version of BGP, right? The HLP island only adds its island ID because it can't express its within-island paths in the path vector. The Scion island adds the AS numbers of all the within-island paths it offers to the AS number field to prevent potential loops. It encloses them in a set relationship to prevent other ASs from thinking the end-to-end path is too long. Finally, the Scion island adds its island ID and establishes a mapping between it and the AS numbers it has added. This informs Scion sources that to pick a within-island path, they must first encapsulate data packets with an outer IP header to cross the D-BGP and HLP islands, D-BGP and HLP gulfs, and then with a Scion header. If there are further Scion islands on the rest of the path, it would need to add more IP headers and more Scion headers to choose the within-island paths in those other islands. So that was just a small sample of our design. There are a lot more fields in integrated advertisements I don't have time to discuss. I just wanted to put them up here. Please see our paper for more details in these other fields, IA processing, and how they enable a variety of protocols to coexist on end-to-end paths. So before I conclude, I want to provide a brief hint of our evaluation. We evaluated D-BGP along a number of axes. We explored how it accelerates benefits. We evaluated its control plane overhead. We tried to understand the difficulty of implementing a basic version of it in Quagga, and we evaluated the difficulty of deploying two new protocols across gulfs and Mininet using this implementation. I just want to focus on how D-BGP, when it is deployed internet-wide, accelerates the rate at which adopters of a specific new protocol see its benefits compared to BGP today without tunnels. So to understand how much D-BGP accelerates benefits, we compared deploying representatives of different types of new protocols in an internet that has D-BGP deployed internet-wide and one that only has BGP deployed internet-wide. We measured benefits as a function of the number of ASs that deployed the protocol. What benefits is depends on the protocol representative being considered. So for protocols such as SION, benefits correspond to a number of total paths to a destination, advertised to potential source ASs that have also deployed SION, right? Because the sources get to pick which path they want to use. Our experiments were done in simulation. Specifically, we used the Bright topology generator to create a representative internet topology with 1,000 nodes. We simulated various protocol representatives by extending a routing simulator that has been used in previous research efforts. ASs that have not deployed a new protocol choose paths with the shortest path length, and we randomly choose which ASs will deploy a given protocol at any deployment level. So here are the results for SION. On this graph, the y-axis shows the number of paths advertised to SION sources to all possible destinations in the topology. It represents benefits at any given deployment level. The x-axis shows the fraction of ASs that have deployed the protocol, and now the blue line will show our results with D-BGP deployed internet-wide, and the black line will show the results with BGP deployed internet-wide. So here are our results. As we can see, D-BGP always outperforms or equals BGP. This is because in a world with D-BGP deployed internet-wide, information about extra within-island paths can be passed through ISPs that only support D-BGP. Whereas an internet without D-BGP, sources running SION will be advertised more than one path to destination, only if that destination is within the same island. So the key takeaway I want you to get from this graph is that D-BGP provides more benefits at low adoption rates compared to BGP. This incentivizes adoption at a time when the new protocol is the most fragile. So we do have results for other protocol representatives. Please look at our paper for details. So to quickly summarize our talk, BGP's rigidity makes it difficult to deploy new inter-domain routing protocols. Via an analysis of 14 recently proposed inter-domain routing protocols, we found that 2 features are sufficient to bootstrap evolvability to a wide range of new inter-domain routing protocols. We incorporated these features into BGP to create D-BGP, and we found that D-BGP isn't actually that far from BGP, and that it can provide significant evolvability benefits. Thank you.
Lauren, TTH, nice talk. I liked it a lot. I have 2 quick questions. The first one is, I was wondering whether you can also with DBGP kind of provide evolvability in the DAA plane. So for instance, if I want to implement, let's say, multicast on top of the internet, could you use DBGP to, let's say, signal multicast group and then populate DAA plane state with it? So you didn't mention much of the DAA plane in your talk, which makes me wonder whether you only support destination-based forwarding like today, or whether you can go a little bit further there.
All right, so let me quickly summarize that question, just to make sure I got it.
Yeah.
So you're asking if DBGP can be used to deploy new functionality in the data plane, right? So generally the answer is yes, because a lot of those really sophisticated protocols I talked about, they basically use different data plane functionality than IP today. Right. So, and then they just send different control information to operate that data plane functionality. Right. So you could have 2 islands using different data planes, right, and have them communicate using DBGP. Yes. Okay. About the specific protocols you mentioned, I'm not entirely sure. I'd have to look.
Yeah, I just made it up, so it's no one.
Okay, cool.
And maybe if I may, just quickly, like, could you comment quickly on the correctness of the protocol that you end up with? So we already know today that BGP cannot, for instance, converge with normal policies between multiple ASs. So what will happen when I will have Wiser, SION, SBGP, BGP, and all of these nice protocols like kind of like running together? Do you think it will ever converge? Can you quickly?
That's a great question. I can't comment on that specifically as to whether this would make convergence problems worse. The one thing I can say is that BGP already provides tons of flexibility in what ASs can do, right? So it's not clear if this is actually making that worse or not.
Okay, thanks.
Ethan Katz-Bassett, Columbia. Neat talk. In thinking about how BGP would need to be modified in order to make it evolvable, did you come away with any kind of lessons on how we can actually move forward given that we have BGP today?
So that's actually really interesting. So let me turn that around into a question about like how would you like incrementally deploy something like D-BGP, right? So what's really interesting about BGP is it has those optional transitive attributes, right, which technically pass through any control information. So the key fixed point from a protocol perspective is actually the path vector field, right? So deploying D-BGP, in my opinion, is about making sure that that path vector field is correct when it is being deployed across, when it's being incrementally deployed at the boundaries of its deployment, right? And there are people, there's been lots of work on like deploying like 4-byte AS numbers instead of 2-byte AS numbers, and they have certain techniques that I think could be used to actually deploy D-BGP itself and preserve the correctness of that path vector field, right? So.
Thanks.
Thanks again. So our